Hey guys, and welcome to another video in my series of videos on statistical mechanics. And in the last video we had just derived this bad boy right here, this pretty useful formula right here, and we finally found out what this Z was that I've been bandying about all this time, not really telling you, being all mysterious and shit about what it is. But now I've told you what Z is. Z is called the partition function, and basically, the partition function it acts like a magic box. That's the way to think of it. It's a thing that you can basically operate on, like for instance, take the log of and divide by beta, which is the inverse temperature, 1 over kBt. I'll just put that. And we showed this gave the Helmholtz free energy of this canonical ensemble. So if you know what Z is, then you can basically get what F is right here. So that is one of these so-called magic box relations, but I'm actually going to go and try and find another magic box relation. So I'm going to start with this right here. F equals minus 1 over beta log of Z. And I'm going to multiply both sides by beta. So I'm going to get beta F is equal to minus ln Z, and I'm going to just bring this minus sign over to the other side, multiply both sides by minus 1, fairly standard. And what I'm going to do is I'm going to differentiate both sides of this equation with respect to beta. Now you might be thinking, well, why the hell are you doing that? How on earth do you even know to do that? Well, you just need to know that this is how you derive it. Not necessarily, you don't need to sort of know how you would have necessarily thought to derive it. Remember, like, this was formulated probably by Boltzmann and a couple of other guys who probably had massive amounts of free time. I'm guessing, gonna go out on a limb here, but I guess you guys don't probably have that much free time. So I'm just gonna show you what they did, which is found to be right. So differentiating log Z beta by beta. So we're differentiating with respect to inverse temperature. So what's this going to be? Well, we've got this minus sign out the front. That's a constant. And we've got beta F. So we've got a product right here. So what's our old friend going to be? We're going to use the product rule. None other than the classic, the product rule. So beta we're going to leave alone, and we're going to multiply that by the derivative of F with respect to beta. We're going to add to that the derivative of beta, which is just 1 with respect to beta, to F right there. And that is the derivative of log Z with respect to beta. So where do we go from here? Well, remember what F is. F is U minus TS right here. But I'm actually going to rewrite this F right here. Instead of writing T, I'm going to substitute this T for beta. F is equal to U minus, instead of T, what's T in terms of beta? Well, that's just going to be S over KB beta right here. So that is what F is in terms of beta. And we're going to take the partial derivative of F with respect to beta. So that is going to be, well, we've got a minus something over beta, so what's that going to go to? That's going to go to a plus the same thing over beta squared. Oops, there shouldn't be a subscript there. I don't know what I was doing. That should be a B, not a beta. Alright, so that is df by d beta, and we have F in terms of beta. So let's go ahead and substitute all this into here. So we've got minus beta. Here's our first beta. What's df by d beta? Well, we got that was just S over KB beta squared. Right there. And you can see that one of these betas is just going to simply cancel. Plus F. Well, F is U minus S over KB beta. So that is what F is. So now all we need to do really is tidy this equation up, and we can see that one of the betas will cancel this down to S over kb beta plus a u minus s over kb beta. And that is still this right here. So, well, look at what happens here. We've got s over kb beta minus s over kb beta. Bam, cancelled out. And so what we end up with, we just end up with u, the internal energy. So what we've now shown is that the derivative of the logarithm of the partition function with respect to beta is simply minus the internal energy. That right here is another magic box relation. Here is our second very useful magic box relation, that the derivative of the partition function with respect to beta is simply the internal energy of the system, and that will be a really good thing that we're going to be using for when we're trying to calculate things like when we have multiple particles, because all these magic box relations, they all work not just for one particle. Here's the cool thing: they don't just work for one particle, they work for many particles, they work for n particles. I've just only considered one particle for deriving these, but you can show that the partition function also applies for many particles, and we'll be moving on fairly soon to the partition function for many different particles, and we'll see how that relates to the one particle partition function. So there we go. Here are our magic box relations, and we can actually, well, we've got the Helmholtz free energy, and we've also got the internal energy. So what else? So from that, we can actually go ahead and derive a load of other really useful stuff. So let's go ahead and do it. So what else can we derive? Well, we know that f is equal to minus 1 over beta log of z, and u is equal to minus d by d beta of log z right here. So, and we also know that entropy is simply u minus f divided by t right there. Or we can actually express the entropy. If you remember our video about my video about thermodynamic potentials, entropy is actually the derivative of the Helmholtz energy with respect to temperature holding the volume constant. It's actually minus this right here. If you remember what the differential of the Helmholtz free energy is. So you can also write the entropy in this form right here. So let's just take an example right here. Let's say we want to work out what the heat capacity at constant volume is. So how do we get that from this z, the partition function? Well, we know that CV is simply the derivative of the internal energy with respect to temperature, keeping the volume constant right here. So what would actually be helpful at this point is to rewrite in this expression right here for the internal energy, rather than as a function of, or as a derivative with respect to beta, it would actually be much more helpful to write it as a derivative with respect to temperature, because remember, beta is essentially a measure of temperature. It's just an inverse measure of temperature, so the higher beta is, the lower the temperature is. And so this is fairly straightforward to do. We can simply use the chain rule and say that dy if y is just some random function that I've just made up, dy by d beta is simply equal to dy by dt multiplied by dt by d beta right here. So actually we only really have to multiply it by this term right here. That's the only real difference between du by dt and du by d beta. So what is dt by d beta? What is this term right here? Well, beta is simply 1 over kbt, so therefore t is simply 1 over kb beta. So dt by d beta is minus 1 over kb beta squared, remember? So we've just differentiated that with respect to beta. And you can actually also write this as, instead of a minus 1 over kb beta squared, you can actually use what beta is. So substitute back in what beta is, because basically we're just trying to get rid of beta. So we can just do a differential with respect to temperature right here. So beta squared, that's going to be 1 over kb squared t squared. And so if we just simply tidy up that fraction, that's going to be minus t squared multiplied by kb, or just minus kb t squared. So that's all we've got to really multiply it by when we're converting. So we actually want dy by dt. So I'm going to just rewrite this equation in exactly the same way. Dy by d beta is simply equal to dy by dt multiplied by minus kb t squared right there. So if we now substitute what y is for log of z, because this is after all what we're trying to do, we get that d ln z by d beta is equal to d ln z by dt multiplied by minus kb t squared right here. But what is d ln z by d beta? Well, that is just from this one right here, that is just minus u. And so the minus signs cancel out, which is quite nice. So therefore u is simply equal to kb t squared d log z by dt. And so we can now differentiate this with respect to temperature in order to obtain the heat capacity. So the heat capacity at constant volume is therefore going to be the derivative of this with respect to temperature. And as you can see, yet again, we have a product, and so therefore we're going to have to use the product rule. So we have that it is kb, and we're going to get a big bracket right here. So let's leave this first term alone, get t squared, and now we're going to differentiate this, and now we're going to get the second derivative of the partition function with respect to temperature. Alright, so far so good, plus the derivative of this, which is 2t, multiplied by d ln z by dt. So there we go. That is the heat capacity at constant volume in terms of the partition function. So if you know what z is, you can just do a couple of those differentials and you will be able to obtain the heat capacity. So this z is a pretty damn useful function. You're able to do quite a fair bit with it. So there we go. That is the partition function in a fairly brief nutshell. Now, so far, we've only talked about non-degenerate energy levels. Now, I have mentioned what degeneracy is. I'll just go through it again. So degeneracy is multiple states with the same energy. And the best way to understand what that basically means is if we draw our ladder right here, as you can see, I've only drawn one state per energy right here. But what if a particle might occupy this state right here? It has exactly the same energy. It's on the same level if this is a measure of energy, but it's got an equal probability of being in this one or this one. And so this has kind of created a little bit of a problem. So say we could also have maybe a threefold degenerate state on this one right here. Basically, we need to count further states, and obviously that is going to affect the probabilities of particles being in a certain energy state, and therefore it's going to affect things like the partition function and the Boltzmann factor and stuff like that. So how are we going to factor in this degeneracy? Well, so going back to the Boltzmann formula for the probability, probability of it being in a particular energy level, EJ, is equal to e to the minus beta EJ divided by Z the partition function, and if I just simply expand out what Z actually is, what our definition of Z, it's the normalization factor. It's the sum from J equals 0 to some arbitrary value J, which is the maximum number of energy, the maximum energy number of e to the minus beta e k. Sorry, that should be a k right there. And the reason that I summed over a different value, a different dummy index, was because I wanted to sum over states. So this right here is summing over states. So it's counting this one, this one, this one, this one, this one, this one, if you expanded out the sum. Which was basically exactly the same as summing over the energies for a non-degenerate system. But as you can see in this scenario right here, we have multiple states at the same energy. So if we sum normally, then we're going to miss out a few of these energy levels right here, which is of course not a good thing. So how are we going to get around this? Well, we're going to now introduce this quantity g of E right here. And g of E is what's known as the density of states. The density of states right here. You can come across slightly different versions of the density of states. You can come across versions which are per unit volume or sort of normalized in some kind of way. But basically the density of states is basically measuring how many times you need to count an energy level again right here. Now in this simple system right here, you can simply see that it's just going to be 3 for this particular energy level. So if I just take this particular energy level right here in our system, you simply have to multiply this level by 3 right here. Similarly, if you wanted to, when you're counting this level, you need to multiply it by 2. And so for the moment, the density of states is going to not have any sort of units. It's just going to be a number in our simple system right here. Normally the density of states is actually a function of the energy itself, and it normally does have units, and we'll get into that a little bit later on. But for the moment, we're just going to call Gj, which is of course the degeneracy, which is the density of states on the jth level. This is just going to simply be a number, so like 1 or 5 or 52 or whatever. So basically we just have to add this extra term, and then we are pretty much fine, really. So let's just go ahead and write out the Boltzmann distribution with this extra term in the denominator right here. So we're going to have e to the minus beta ej as normal. But when we're summing over the states to work out the partition function, we can now sum over j. We're now going to sum over the energies, just like we were able to do in the non-degenerate case. But this time we're going to have to add this g right here. So gj e to the minus beta ej. So now we are summing over energies like we were before. So we're not summing over states this time, we're summing over energies. And this formula right here is exactly the same as this formula right here. So basically you're just summing over different things, and this is what this little g right here is telling us. It's telling us how many times do you have to sum over this particular energy level. So that pretty much nearly wraps up the Boltzmann distribution and the partition function. I'm going to go over just a couple of examples to show you how to use the Boltzmann distribution to calculate sort of various different probabilities and stuff, because the Boltzmann distribution is pretty useful for a lot of sort of real world applications. And so I'm just going to go over a couple of examples as to how you'd use the Boltzmann distribution for various energy levels. So the first example I'm going to do is going to be related with magnetic resonance imaging. And what I'm going to draw is I'm going to draw a set of two energy levels. And these two energy levels are actually created due to the presence of a magnetic field. The magnetic field actually causes what's called splitting due to the spin of the proton, and therefore they can take two different energy levels. And so I'm going to just draw in the normal energy state right here. This isn't actually a valid energy state, so that's why I've drawn a dotted line, but this is what it would be if there was no magnetic field, basically. So you have two different energy states, and this energy difference right here is, I'm going to call it mu b right here. Now mu is known as the magnetic moment of the proton, and you don't have to know really what that is. Basically a measure of how much energy a proton gains in response to a magnetic field. So yeah, and B is, you probably do know this, B is just the magnetic field that is applied. It's sometimes called the magnetic induction, but I'm just going to call it the magnetic field for now. So this right here is a new energy state that has been formed by the applied magnetic field right here. So this is one energy state that the proton can have, but it can also have this other one right here. And the reason why it has two is simply because of the spin alignments of the protons. And so this is going to be exactly the same distance, except it's going to be minus mu b right here. This state right here is just the zero state. It's what's known as the ground state. So this proton has a spin up state, and this proton has a spin down state. And the question I want to ask is, when this system is in equilibrium, what is the ratio of particles that are in this spin up state to spin down state? So how are we going to work out what this is? Well, we're going to use our old friend, the Boltzmann distribution. So let's have a look and ask ourselves, what is the probability that the proton is in the spin up state? So what is the probability that it has the energy of the spin up state? So we're going to use the Boltzmann formula right here. So we're going to get e to the minus beta. But what is the energy of the spin up state? Well, the energy of the spin up state is just mu b. So instead of writing e, I'm going to substitute e for mu b right here. And this is divided by the partition function z. So this is the probability of a proton being in the spin up state. So what about the spin down state? Well, probability of it being in the spin down state is simply going to be e to the minus beta, but instead of mu b, it's going to be minus mu b right here, because this is, of course, the energy of the spin down state. And this is all divided by z right here. So we want to know what the ratio is between protons in the spin up state and protons in the spin down state. So how are we going to work out what that is? Well, we've got two formulas right here for the probability of it being in the spin up state and the probability of it being in the spin down state. And I hope you can see that the ratio of the actual number of protons, let's just call it R for now for ratio, the ratio of the number of protons is simply the ratio of the probabilities. So if we want the ratio of spin up to spin down, then we want the probability of it being in the spin up state divided by the probability of it being in the spin down state. So if something's twice as likely to be spin up than spin down, then the ratio is going to be 2 right here. So that is what we're going to use. And when we substitute this in, something pretty cool happens right here. So the probability of it being spin up is e to the minus beta mu b divided by z. And we're going to divide all of that by e to the, well, these two minus signs just cancel out, so it's going to be e to the beta mu b divided by z. And look what happens to these z's. They are the same z's. We're assuming that these are non-degenerate, so therefore these z's just simply cancel out. And therefore we can simplify this exponential to be e to the minus beta mu b multiplied by e to the minus beta mu b. So what I've done right here is I've taken this one in the denominator and I've simply brought it upstairs, but in doing so I've changed the sign. And using the additive property of exponentials, we can simply add these two together. So we're going to get e to the minus 2 beta mu b. So this right here is going to give us the ratio of particles in the spin up state to the spin down state. And of course you can see that there's a temperature dependence on this. So it's not just simply going to be 1/2, it's not going to be equally distributed, but you can see that there is obviously a temperature dependence on where these particles are going to be sitting. So what I'm now going to do is I'm now going to do a little bit of a mathematical cheat, and it's called the binomial expansion right here. And it's a fairly well-known one in maths, and basically it says that e to the power of x is simply approximately equal to 1 plus x. In fact, it's actually called the Maclaurin expansion of e to the x, and this is just the first two terms of the Maclaurin expansion. You actually do get several more terms if you do the full expansion, but basically that is a fairly well-known mathematical trick you can do. You can do a Maclaurin expansion of e to the x, and you get 1 plus x squared plus x cubed, and so on and so forth. So I'm now going to approximate what this term is right here using the Maclaurin expansion. And so we can simply see that that's equal to 1 plus x. Well, what's x? Well, x is actually going to be this whole term right here. So it's actually going to be a minus rather than a plus. 1 minus 2 beta mu b. So, and there's also going to be some other terms, but we're not going to worry about that. So this ratio is approximately equal to 1 minus 2 beta mu b. So what are we going to do with this? Well, we can't really do too much more unless we actually kind of know a few of these values. So we know, so the proton magnetic moment is fairly well known. It's 1.41 times 10 to the minus 26 joules per Tesla. Typical magnetic field strength in like a hospital is about 1 Tesla. And the temperature, let's say it's room temperature, so let's just call it, I don't know, about 300 Kelvin. So what is this R going to turn out to be? Well, R is going to be 1 minus 2. So what's beta? Well, beta is 1 over kBt. Kb is, of course, 1.38 times 10 to the minus 23 right here. Joules per Kelvin, of course. So what is 1 over a very, very tiny number? Because the t is not going to make a huge amount of difference to that. 1 over a really tiny number is going to be a really, really big number. So therefore beta is going to be quite a big number, but it's actually going to get cancelled out almost entirely by the fact that this right here is a very, 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 very small number. This is just 1, so we don't have to worry about it. So it actually turns out that this term right here, this 2 beta mu b, is actually very, very small for typical conditions. And so therefore you find that the ratio is just simply 1. It just basically cancels down to 1. And that's kind of what you'd expect. You know, you'd expect that the probabilities of it being in the spin up state and the spin down state are roughly equal. So there's actually the same number of protons up here as there are down here. And what that's kind of saying is that the temperature is not really important enough in order for it to affect whether they're going to be in the spin up or the spin down. The temperature is not quite low enough, really. If the temperature was a lot lower, then beta would obviously be much higher, and if it was a bit higher, then it would be able to cancel out this term right here a little bit more, and so therefore you'd be able to see that for for lower temperatures, much more protons would occupy the ground state rather than being equally distributed like they are here. So there you go, that's one example of the Boltzmann distribution being used. I'm going to do one more example. This example might be a little bit easier, and we're going to go and imagine that we have an atmosphere right here, and of course in the atmosphere we're going to have loads and loads and loads and loads of particles just sort of whizzing around right here. So here's our atmosphere, here are our particles, and we'll ask ourselves, what is the ratio between the probabilities of the molecules being at this height to this height right here? Now let's call this height, let's just give it an arbitrary number, let's call it, I don't know, 1,000 meters. So that difference right there in height, so this is a measure of height, is just 1,000 meters. So we don't know what these two heights are, but we do know that the difference between them is 1,000 meters. So what is the ratio of particles at this level compared with what there are at this level? So let's go ahead and use our Boltzmann formula again, that the probability of being at, let's go ahead and let's start with the bottom energy level, E1, which is going to correspond to H1, is simply equal to e to the minus beta E1 divided by the partition function. And the probability of it being at height H2, hence having height of energy E2, is equal to e to the minus beta E2 divided by the partition function. As you can probably see, the partition functions are yet again going to cancel when we take the ratio. So what is the ratio? Well, let's go and substitute that in. E to the minus beta E1 divided by e to the minus beta E2. So the z's have now gone. We've just simply got a ratio of exponentials. So let's go ahead and substitute what E1 and E2 are in terms of H. So what is the energy? The energy, we can I hope you guys can see that this right here has more energy than this right here because it's higher. It's got more gravitational potential energy. So we're going to use the formula for gravitational potential energy, that is mgh, and we're going to assume that all the molecules have the same mass. So E equals mgh, and this is how we're going to relate the height to the energy. So the ratio is now e to the minus beta, instead of E1 we're going to write mgh1 divided by e to the minus beta mgh2, and therefore now you can take this denominator and bring it upstairs, and it will now become e to the minus beta mgh1 multiplied by e to the beta mgh2, and therefore you can now therefore combine these two exponentials to give e to the beta mg brackets h2 minus h1 right there. So we can't really get any further without putting in some values. So what's the temperature? Well, let's assume room temperature yet again, 300 Kelvin. So that makes beta is going to be something along the lines of it's going to be sort of 1 over about 10 to the minus 21. So that's beta is going to be approximately 10 to the 21, just very approximately. The mass, well, what's the mass of one individual particle? Well, that's going to equal the molar mass of O2. So the molar mass of O2 divided by the number of molecules. Well, that's going to be simply 5.31 times 10 to the minus 26. That is the mass of one O2 molecule. So that's the mass, and we know that H2 minus H1, well, we didn't know what H2 and H1 were, but we actually do do know the difference, so therefore we can simply substitute in h2 minus h1 is equal to 1000 meters. And if you substitute all of that into this formula right here, you find that R, the ratio, is equal to 1.13. And so you find that at any point in the atmosphere where there's a 1000 meter gap and the temperature is 300 Kelvin, then the particles are 13% more likely to be found at this lower level than they are at this upper level right here. So there you go. If you're interested in that, then there you go. Now you know. If you're not interested in that, then that's fair enough, because it's really not that interesting unless you're an atmospheric scientist. I'm sorry to all the people who I've offended. Yay, go me!